In this video, we'll derive the equations for Lagrange multipliers. So hopefully you've watched the last Mathematica video already where we kind of went through pictorially what we expect to happen. So if you remember, what we looked at is a function. What we want to do is we want to extremize, which again means finding the max and min values. Right? So we want to extremize the function f, and we'll derive here, well actually it doesn't matter how many variables, but let's say here we'll do it for x, y, z. It could be just x, y, it could be 4 more variables. Right? So we want to extremize this function f subject to constraints, well the constraint, just one constraint, g of x, y, z equals c. Right? So what we're saying is, among all of the points that satisfy this equation, which of those points gives f its biggest value and its smallest value? Right? So in the Mathematica video, what we looked at is these extrema should happen at points where the gradient of f and g are parallel. Okay? Now that is true. That is where they happen. But before we can just start saying, yeah, okay, that's what happens, and then just go from there, we have to show that, yeah, that really is where they happen. And then we have to set up how to solve that kind of problem. So what do we do? How do we do this? So what we can do is suppose P is an extreme point. All right? So what that means is at P first off should solve this constraint equation. And second, F should either be a maximum or a minimum at P when we restrict it to this level surface. Right? And again, it could be a level curve if there's no z's. Right? So, well, what does it mean? What can we get here? Here's some things that we know. What we're going to do is let r of t be, and there's a key word here, let r of t be any curve passing through P. Right? So this constraint, in this case, this is a level surface. So that curve here lies entirely on that level surface. And we're saying that it passes through here. And in fact, I want to be a little more specific, i.e. r of t naught equals P. Right. So it has to pass through P at some time. Let's say that time is t naught. Okay, so then, well, one thing we know, and this is actually independent of P being an extreme point, we know that the gradient of G at P is perpendicular to R prime of T naught. Right? Because the gradient's always perpendicular to the level surface. All right, so we have that. That's good. But we need to get f involved in this situation. So how can we do that? Well, what we can do is we can actually restrict f to the curve r of t, right? Because since r of t lies on the constraint surface, then restricting it to that is just restricting it to a piece of the constraint. Okay, so let's define a new function, h of t, and we're going to define this to be f of r of t. Okay? And since r of t lies on the surface, and p is a maximum of f, well, a maximum or a minimum of f on the entire surface, well, then since the curve is a part of the surface, that means it's also a maximum here. So what does that mean? Well, that means the derivative of h has to be 0 there. So first let's say let's compute the derivative of h. So h prime of t is gradient of f at r of t dot product with r prime of t. Okay, so here's where it's useful to remember the chain rule. Okay. Well, so since h has a max or min, we don't know which one it is, has a max or min at t0, h prime of t0, which is gradient of f at p dot product r prime of t naught. So remember, r of t at t0 is p. Right? This has to be 0. But geometrically, what does that mean? We have a dot product of two vectors being 0. So that says that the gradient of f at p is perpendicular to r prime at t naught. But here was that key word that I mentioned earlier. This is any curve passing through that point. So it can pass through that point in any direction, which means that this can be any tangent vector to this surface, which means, and this is the same way we showed it before, the gradient of f is perpendicular to this level surface. Right? That's how we showed that the gradient of g is perpendicular, by showing it's perpendicular to every tangent vector. So we've done that again. So what does that mean? Well, that means the gradient of f is perpendicular to the surface. So this is perpendicular to the level surface at p. Well, there's only one perpendicular direction to a surface, so what that actually tells us, so therefore, actually, the gradient of f at p is parallel to the gradient of g at p. In other words, gradient of f at p is lambda times the gradient of g at p. So that has to be true at a maximum or minimum. And that's what we saw and suspected from the graphs of these things, from the contour plot of f and this constraint. Right? That's what we expected in the Mathematica visuals. Right? So where this section gets its name is from this guy right here. This is called a Lagrange multiplier. Let's kind of summarize real quick what this process is. Okay? So we'll put it over here. So to extremize f subject to some constraint, g equals c. All right, so to extremize this function f subject to this, we solve given by gradient of f is lambda times the gradient of g, and g equals c. Right? So what that's saying is we're looking for points on the constraint where the gradient vectors are parallel. Right? And from among those points, one is the max, one is the min. All right? And then to figure out which one's which, you just have to plug them into the function f and compare values. Okay? So in the next video, we'll do the example from the Mathematica code, and see you there.